Let's take a look at this one. Li solid plus SN CO4 aqueous. So the first question we ask ourselves is, what kind of reaction is this? Well, we've got an element and we have an aqueous solution. What kind of reaction dealt with an element and an aqueous solution? We call those single displacement reactions. Single displacement reactions means we have to have the charges of all three ions that are involved here. These are ionic compounds that we're dealing with. Lithium is a metal in group 1A, so it's positive 1. Tin is a metal in group 4A, so that's positive 4. Oops. So that means that this is not correct. We need to put a 4 right there to balance those charges out, because ClO4 is negative 1. So, don't worry, on the practice problem, I'll have that correct on there for you. That should have been the parentheses 4 outside of it. Alright, now, what's going to happen here? Well, the positive is going to kick out the positive, so the SN is going to be kicked out by itself. And then the Li is going to go with the ClO4. Now, the parenthesis 4 was put there because of the charge had to be balanced out. We may or may not need the parenthesis in the 4, but we're going to assume no for right now until we get to the charges on the other side. Okay? Well, in this case right here, we know that tin is going to be a solid because it's a metal. The only metal that's not a solid is mercury. And this is going to be aqueous because we have an aqueous solution here. We always end up with an aqueous solution in a single displacement reaction. We always end up with an element, whatever phase that is, and then the aqueous solution for that. Alright? Now, let's make sure we got the right equation. So let's put the charges on there. Positive 4, positive 1, negative 1 from what we got over here. And look, charges balance out. So that's the correct formula for lithium perchlorate. Now we got to balance the equation out. Li is 1, Sn is 1, ClO4 is 4, Sn is 1, Li is 1, and ClO4 is 1. Well, obviously the ClO4 is not balanced yet. I'm going to use the red pen because it's getting a little crowded over there and you can see this clearly. So that means you need 4 ClO4s. But I can't put a 4 in the middle of it. It's got to be in front of the entire compound. So we have to put a 4 right there. So that does change the lithium to 4 as well as the perchlorate to 4. So this is not balanced yet because the lithiums now are not balanced. So to get this balanced, we have to put a 4 for the Li right there. And there, ladies and germs, is our balanced equation. Okay, let's do another one. Let's take a look at this one. This one might be pretty easy. C6H6, liquid, plus O2 gas, yields CO2 gas, plus H2O liquid. Wow, when you see those products, you know right away what this has to be. And what's that? Combustion. You know, burning with oxygen, creating carbon dioxide, and voila. So, combustion. Alright, so we don't need to do anything outside of balance the equation. Everything else is laid out for. Actually, if I should have done this. Say, okay, this is what we have here. What kind of reaction is it? And the fact that you have an organic compound with oxygen should have told you that it was combustion from there. And the product will always be CO2 gas plus H2O liquid. So look out for that. I won't give you the full equation. That was a mistake on my part. Alright, anyway, moving on. So we have 6 carbons here, and 6 hydrogens here, and 2 oxygens here. We got 1 carbon here. We got 2 hydrogens here, and we got 3 oxygens here. So deal with the 6 here for the carbons. So we put a 6 there. The carbon's the same. Deal with oxygen later. Hydrogen is 6 here and 2 over there. So to balance that out, we put a 3 right there. Now we add up. We got 12 oxygens there and 3 oxygens there for a total of 15. That makes that 15. And the number that's going to change 2 to a 15 is 15 over 2. Oh, I hate fractions. That's just too easy. Oh, don't make it so easy, Mr. Campbell. That's awful. All right, so there you have a combustion reaction. Next one. Magnesium nitrate. Aqueous. Plus potassium oxalate. What kind of reaction is this? Well, you got 2 aqueous ionic compounds. It has to be double displacement. And in double displacement, you have to find the charges of all 4 ions. Magnesium, group 2A, positive 2. NO2 is a polyatomic ion. You find that on the chart. You see that the charge for that is -1. Potassium is a metal group 1A, so that's positive 1. C2O4, the oxalate ion, is a polyatomic ion whose charge is -2. So, that means then that the Mg and the K, forget the 2, because the 2 is not normally part of the K, it's just there to balance the charges. But the K and the M2, or Mg rather, are going to switch places. That means the K is going to go with this. Now notice that the NO2 has a parenthesis 2 around it. That's not normally part of the ion. It has to normally be part of the ion to begin with, so we're just going to put NO2. We may need a parenthesis at a 2 or a 3 or whatever, but we'll figure that out once we get to that point. Plus, then the Mg goes with the C2O4. We're going to have to have phase here, we're going to have to have phase here, and we're going to have to balance it at some point. So, let's do the charges first to make sure we got some. We got right there in our faces. Potassium, we said, is positive 1. Nitrite, we said, is -1. Look, they're already balanced. We didn't need that parenthesis of 2. It's fine the way it is. Mg is positive 2. Oxalate is -2. Oh, look, the charge is added to 0. We don't need anything for that either. Okay? Now, let's deal with the phases. Potassium is a group 1 metal. That's aqueous. NO2 is also always aqueous. So this is our aqueous compound, and this is going to be our precipitate, the one that we're going to see producing snow in our beaker. Now we balance the equation. Again, with the line representing the arrow over there. Left-hand side, Mg, 1, NO2. We got 2 of them. K, we got 2 of them. And C2O4, we have 1 of them. Come over to this side here. K, we have 1. NO2, we have 1. Mg, we have 1. And C2O4, we have 1. Wow, that's pretty easy to figure out. The K and the NO2 are both 2's. So if I put a 2 over here, that's going to change this K to a 2 and this NO2 to a 2. That balances it, and there is your answer for your 4th problem, your double displacement reaction. The last one I want to do is the 5th reaction that we did in this chapter, and that is going to be shown by taking K and oxygen. K is a solid, oxygen is a gas, and you're going to be asked to complete this and identify the type of reaction it is. Well, if you take 2 elements and that's it, there's only one thing you can do with them, and that is synthesize a compound. So this is a synthesis reaction. Okay? So if it's, because we're going to synthesize it, we have to make sure the charge is at 0. So we need to find what the charges are before they even. So we look for the charges here. We go to the K. The K here is in metal group 1A, so that's positive 1. Oxygen is a non-metal in group 6A, so it's 2 away from 8. And non-metals are negative, so this is -2 because it's being 2 away from 8. So we put these together, we ignore the 2 because the oxygen is diatomic by itself, but not necessarily in a compound. So put K and O right there. Bring these charges over. And we see that the charges are not balanced. And you can probably tell here that we're going to need to have 2 potassiums in order to balance the -2 charge. So we're going to put a 2 right there, a subscript 2 by the K. Next thing we need to do is to figure out what the phase is. This is an ionic compound because potassium is a metal. And all ionic compounds are solids. Next thing we need to do then is to balance the equation. We have 1 K, we have 2 oxygens, we have 2 Ks, we have 1 oxygen. So if I do the option first, if I have 2 here and a 1 here, I'm going to put a 2 in front of the K2O. Make that 2, but now potassium is 4. So now I'll put a 4 in front of the K over here. And that is balanced. Now that's just one of 2 ways we could do that. We could have started with the oxygen by putting a 1/2 here and a 2 here and nothing over here, and that would have been just fine. Regardless, we've identified the type of equation this is, type of reaction. We have to make sure that we grab the charges for the synthesis reaction, make sure they add up to 0 over there, and then balance the equation. Make sure also that you understand that when you're looking at these, there are little tip-offs as to what's in the reactants to determine what kind of reaction you're going, and then make sure all reactions are balanced, make sure all diatomics are understood, all phases are understood. And there you have it. So, you have practice problems that are attached to this. Have fun!